Hey guys, it's Wilson, and I wanted to talk to you a little bit about the project you guys are getting into. So you can see a picture on the assignment sheet that shows what the tester is going to look like. But simply put, what you're going to get into is making a beam, and beam looks like this. And we are going to push down on it. It's going to be supported here and here. And you guys can kind of figure out what's going to happen is it's going to bow down like this, and it's going to bow down like that when we press. Now, here's what's interesting. On the top half of this beam, it's going to compress. If you think about, if you even do it with your hand and kind of squeeze your hand into sort of a shape like this with your fingers, you're going to get little wrinkles here. So the top here, we have compression. And on the bottom, we have the opposite. You can actually see the wrinkles in your hand straighten out over here. So what we're seeing is tension. Now, if this was a French fry, you can crush a French fry, or you can rip a French fry apart. So either one of these forces that act on it are going to cause a potential failure. Now, interestingly enough, we have a line through the middle of the part here, and this is called the neutral axis. The neutral axis is where there is no compression, there is no tension, it's just flexing there, or deflecting. So if you imagine this was just a piece of paper, that single piece of paper would not stretch or compress. But if we had a bunch of pieces of paper on top, they'd have to get smaller, and a bunch of pieces of paper under that, they would actually have to stretch and fall apart. Again, just like what we're used to seeing in our hands. So, how do we figure out where this line is in the part? You guys actually already know how. It is the centroid. So, if this part had a cross-section look like this, you might be able to guess that the centroid is here, which would be here and here. And that is actually where the neutral axis is. So here's what that means. That is where this thing will not compress and will not experience tension when you press on it like that. Oop. Come back. Okay. So the further something is away, this way or that way, the more compression or the more tension it's going to experience. Now, the more material you put over there is important as well. What you guys may have seen before as an alternative to this solid cross-section is making something that looks a little bit more like an I-beam. Now, if this was the cross-section of our structural member, We might go as far as to assume that our neutral axis is right here. Again, that's going from this point to that point. So lots of compression here, lots of tension here, but there's lots of material there to resist that movement. So this is an I-beam, and this is why it has a lot of strength. As this thing wants to deflect, again, it's going to go down like this, and it's going to go down like that. Again, this is if we're forcing down in this direction. So we're going to have compression here. We're going to have tension here. And if you put lots of material here, it's going to be hard to compress. And here it's going to be hard to draw tension against that material. So this thing is strong, but we have removed a bunch of material here and here. So it's light. And this gets us to that efficiency. Remember, our efficiency is going to be pounds per dollar. The more pounds you hold, the better efficiency score you're going to have. And the less dollars, and dollars here is $5 per cubic inch. You guys remember the volume command in Inventor? You can actually calculate exactly how much your device is going to cost. And there we go. That's some of the basics, guys.